Okay, so I'm just going to run through a little bit in this video about the reference circle. So when we've been looking at simple harmonic motion, we're talking about something either oscillating up and down, so a mass bouncing on a spring, or we could be talking about things oscillating from side to side, so something like a pendulum, or in class we saw the little cart attached to the spring oscillating backwards and forward. Now, in that situation, the problem that we have is that when we're looking at various positions during our simple harmonic motion, so if we think about something oscillating from side to side, we know that it's not constant velocity. And that can become a problem when we're trying to work out how far something's travelled in a certain amount of time, or indeed how long it's taken it to travel a certain distance. So if we think about our oscillation, we've got an amplitude for our oscillation, which is how far it is from here to here, or if we're going vertically, how far it is from the top of the oscillation to the bottom of the oscillation. We've also got our time period, so that's how long it takes to go from here to here and back again. Okay, so when we're looking at, say, maybe how long it takes to go from here to here in just half the time period, or indeed if we're going to go from here to here, we can just do a quarter of the time period. The difficulty comes when we look at intervals along here. We can't just keep dividing it equally, and this is because it's not constant velocity. So we know out here we're going to have v being 0, in the middle we're going to have v being a maximum, and our acceleration out here is going to be a maximum. Acceleration here is 0, acceleration here is going to be a maximum. So what we need to do is find some way of working out where these various positions are going to be at a certain time, or how long it's going to take to move a certain distance along here. And that's basically what we use the reference circle for. It's just a sort of mathematical and in some ways a visual aid to help us understand what's going on and be able to calculate various parts around our circle. So if we carry on thinking about this oscillating motion from side to side, we can represent that as our reference circle. That's a terrible circle. So across the diameter of our circle here is going to be the amplitude of our oscillation across here. Now, if we think about something moving around the circle, and we always move around the reference circle in a clockwise direction, we can think about something moving around the reference circle and something going across our oscillation at the same time. So if we have these two little spots here, so our blue spot is going to move across the circle at the same time our little black spot is moving anti-clockwise around the circle, and if they both go at the same speed, they track each other across and they carry on. This one will go back again, and this one goes around the top of the circle and they'll come back. So as your blue spot goes from here to here and back again, the black spot will do one complete revolution around the reference circle. Okay. So the time it takes to do one oscillation across here will be the same as the time it takes for the black circle to go all the way around our reference circle. So usually we will be told the amplitude of our oscillation, so that's going to be this distance from here to here. Okay. Now if we think about how that relates to our circle, that's also going to be the radius of our circle. I'll draw that in black, okay, because that's related to our circle. So as our little spot moves some distance along here, obviously our black spot will move along its circle. So if we've gone here, our little black spot will be here. So that will have moved around this far. In the same time, our blue spot has moved around here. So we can use the fact that we know this distance, the radius, is also going to be our amplitude, to work out what angle this has moved through in the same time that this blue spot has moved to this position. And then it's just a case of using some trigonometry and some Pythagoras to work this out. Okay. So we can work out the angle that this is turned through. Okay, so if we look at this equivalent triangle here, okay, we're going to have a distance here which I'm just going to call y for now, and we've got the amplitude here. Okay, so if we think about our angle, think about alternate angles here, it's going to be the same one here. We've got hypotenuse and we've got the opposite. So sine theta is going to be equal to y over a. So we could work out that angle theta here. And then if we want to think about what this means in terms of our time period, we also know that if we can work out that angle theta, we know that that is a fraction of our whole circle. And that's going to be the same ratio as the time it took to move through that angle compared to the total time period, which is the time it takes to do one complete oscillation. And we can use this then, as long as we can work out the angle and we know the time period, we should be able to use this to work out any time it takes to move a given distance. Now this particular example is looking at something moving from the equilibrium position in the middle here, but you could just as easily do this working from either end, or you can in fact turn the whole reference circle round and do this in the vertical orientation. And so then you'd be looking at your, in fact if we just do that, okay, this would be like you know, mass on a spring bouncing up and down, and you're going to be going up and down. Here's your equilibrium position. Okay, so this one you'd be moving a certain distance below equilibrium. Okay, and so that's, I guess, the basis of what we're going to use our reference circle for.